In today's video, we will be building the high-level design of a YouTube-like video platform. Now, if we go through our design specifications, we can see that the system needs to handle around 1 billion video views per day and approximately 500 hours of video uploaded every minute. It also needs to support adaptive bitrate streaming and global delivery while keeping the video startup time below 5 seconds. The main challenge here is handling the enormous amount of video data and bandwidth. So, this architecture separates the upload and processing pipeline from the actual video delivery path. Now, let us start building the architecture. First of all, we have a client. As we know, everything begins with a client, therefore it is the first component. The client can be a web browser, a mobile application, smart TV, or any other device which is used to upload or watch videos. Now, there are essentially two major operations happening from the client side. The first is uploading a video and the second is requesting a video for a playback. For these two operations, both follow different paths in our architecture. For uploads, the request goes through the client to the API gateway and further to downstream services. But for video playback, the API gateway eventually routes the delivery request towards the CDN, which serves the actual video content to the client. So after the client, we have the API gateway. The API gateway acts as the entry point for the application's backend requests. When a user uploads a video, the request first reaches the API gateway. The gateway then handles common responsibilities such as authentication, request validation, authorization, rate limiting, and routing. And once the request is validated, it is forwarded to the load balancer. The API gateway also has a connection towards the CDN for the video delivery path. So for the normal upload requests or video upload requests, the request goes from the client to the API gateway and then further to downstream services. While for the video read requests, it goes from client to the API gateway and the API gateway sends those requests to the CDN and the CDN serves the video to the client. The important distinction here is that the API gateway is not responsible for transferring the actual video bytes for every playback request. The CDN is responsible for that because serving massive amounts of video traffic directly through the application servers would not scale. Then we have the load balancer. The load balancer receives the upload requests coming from the API gateway and distributes them across multiple upload service instances that we have. We have two upload service instances in this architecture as we can see, and having multiple instances allows us to scale horizontally. If the number of uploads increase, we can simply add more upload service instances behind the load balancer rather than depending on a single server. Therefore, the load balancer helps to distribute the upload workload and prevent one upload service from becoming a bottleneck. The upload service handles the application's video upload processing. When a user uploads a video, the request reaches one of these upload service instances. The service validates the upload and then sends the video processing job into the transcoding queue. So next we have a transcoding queue. The important part here is that the upload service does not perform the expensive transcoding itself. The video transcoding can consume a significant amount of CPU and can take a considerable amount of time, especially for large or high resolution videos. So instead of making the user wait for transcoding to finish, the upload service places the job into the queue and allows the processing to happen asynchronously. This keeps the upload path responsive and allows the system to handle many more uploads concurrently. So this transcoding queue right here helps us to decouple the upload services from the actual video processing. Whenever a video upload is received, a transcoding job is placed into this queue. The job can contain information such as uploaded video's location, video ID, and different processing operations that need to be performed. The queue is useful because uploads can happen in bursts. For example, if thousands of videos are uploaded at the same time, the upload services don't have to wait for the transcoding workers to become available. They can simply place the jobs into the queue. The transcoding workers can then consume these jobs at their own processing capacity. Then we have the transcoding workers. The transcoding worker performs the heavy video processing. It consumes jobs from the transcoding queue and processes the uploaded video. This is where the original video can be converted into multiple resolutions and bit rates. For example, a single video uploaded could be transcoded into various versions such as 144p, 360p, 720p, 1080p, and 4K depending on the source video and platform's requirements. This is important because our platform needs to support adaptive bitrate streaming using formats such as HLS or Dash. Instead of sending one huge video file to every user, we generate different versions of the video. During playback, the client can switch between these versions depending on the user's network bandwidth and device capabilities. For example, if the user's connection is strong, the player can request a high bitrate 1080p segment, while if the connection becomes slower, it can switch to a lower bitrate version. This helps prevent buffering while maintaining the best possible video quality. The transcoding worker has three important outgoing connections in this architecture. As we can see right here, the transcoding worker is connected with the original storage, the metadata DB, and the metadata cache. Now, the original storage is where the video files are stored. Video files are extremely large compared with normal application data, and for that reason, we need scalable object storage rather than storing video files directly inside a relational database. The transcoding worker writes the processed video content into this storage layer. The different video representations generated for adaptive streaming can be stored here and later served through the CDN. This storage layer needs to be highly durable because videos are long-lived assets and should not be lost. Then we have the metadata database. The metadata database stores information about the videos rather than the actual large video files. For example, it contains the video ID, title, description, owner, duration, available resolutions, and more information about the available HLS or dash representations, and many more. The transcoding worker updates this database after processing the video. This metadata is important because when a user wants to watch a video, the system needs to know which video exists, where its different representations are stored, and which versions are available for playback. The actual video bytes remain in object storage rather than inside the database. Next, we have the metadata cache. The metadata cache is used to keep frequently accessed video metadata in memory. Imagine a popular video being watched by millions of users. We don't want every playback request to repeatedly query the metadata database for the same information. So the frequently accessed metadata can be stored in the cache memory. The transcoding worker updates the metadata cache after processing the video, and later when the platform needs information about a popular video, the metadata can be retrieved much faster from the cache instead of repeatedly hitting the database. This reduces database load and improves the responsiveness of the playback path. Now let us talk more about the CDN. The content delivery network is the most important component for handling enormous amount of video traffic generated by this platform. As we know, the requirement is around 1 billion video views per day, and the platform needs to serve users globally. So it would not be practical to send all of this traffic directly through our application servers and storage. So instead, the CDN caches video content at edge locations that are geographically closer to the users. For example, if a user in India watches a popular video, the video segments can be served from a nearby CDN edge cache instead of requiring the request to travel all the way back to the original storage location. This reduces latency and significantly reduces the load on our storage infrastructure. The CDN is also what allows us to handle millions of concurrent video streams. At last, we also have a monitoring service. So all the important components in our architecture are connected to the monitoring service, and the monitoring and alerting service is responsible for keeping a track of all our important components. So this is the entire architecture right here, and let us now summarize the architecture. First of all, let us go through the upload path. The request starts at a client, and from the client it goes to the API gateway. The API gateway handles authentication and request validation and forwards the request to the load balancer. The load balancer distributes the request to one of the upload service instances that we have. The upload service accepts the upload and creates a transcoding job, and instead of performing transcoding synchronously, it places that job into the transcoding queue. Transcoding worker consumes the job from the queue and processes the video and generates the required resolutions as well as bit rates for adaptive streaming. After the processing is done, the worker then stores the processed information into the original storage and the metadata into the metadata DB as well as the metadata cache. So the upload processing path is the client, then API gateway, then from API gateway to the load balancer, then to one of the upload service instances. Then a job is created at transcoding queue. From there, a transcoding worker picks the job, and then the information is stored in the original storage, metadata DB as well as the metadata cache. The major benefit of this design is that uploading and transcoding are decoupled from each other, so the pace of uploading cannot affect the pace of transcoding. Now let us look at what happens when a user requests to watch a video. First of all, the client requests the video through the application's API path, and the request reaches the API gateway. The API gateway handles the application level request and routes the delivery path towards the CDN or content delivery network. The CDN is responsible for serving the actual video content to the client. When a user starts playback, the video is not necessarily downloaded as a one massive file. Instead, with HLS or dash, the video is divided into smaller segments or subunits at different resolutions and bit rates. The client initially requests an appropriate stream from the CDN, and as the playback continues, the client continuously evaluates the available network bandwidth and can request higher or lower quality segments depending on the the network speed. For example, if the connection becomes slower, the player can switch from a 1080p stream to a 720p or 480p stream. If the bandwidth improves again, it can move back to a higher quality representation. This technique is known as adaptive bitrate streaming. Because CDN is geographically distributed, these video segments can be served from nearby edge locations instead of repeatedly accessing the original storage. This is what allows the platform to support global delivery and maintain a low startup time. We can then run our architecture, and we can see that we got a perfect grade because we met all our requirements. We can also test out this architecture's performance in Murphy's lab. And when we exit Murphy's lab, we get a performance report of our architecture. Now, one important point to keep in mind is that we can scale up our architecture even more or make it faster by having multiple transcoding workers or by adding more upload service instances. But we had a budget constraint of $24 per hour. And by keeping that budget constraint in mind, this is the most optimal architecture that we have designed. So this is the basic design for a YouTube or video streaming platform.